everyone, welcome into lecture number 11 of linear algebra. This lecture is on matrix representations of linear transformations. So let's start by reviewing a fact that we learned in a previous lecture, which is that if we have a matrix, so a matrix A, let's let A be an m by n matrix, so A is in Rm by n, then the function defined as follows, and we verified this in an exercise, I believe, after a previous lecture, but the function L of x, or the mapping we might say, defined by A times x, just matrix multiplication. So this is a linear transformation. And remember, that means you just have to check the two linearity conditions, right? But this is a linear transformation from Rn to Rm. So that means that it takes vectors in Rn, x has to live in Rn, and it returns a vector in Rm. So A times x is a vector in Rm. All right, and because of the properties of matrix multiplication, this defines a linear transformation. So what we'd like to study in this lecture is kind of the converse of this, which is, given a linear transformation L, can we find a matrix A which represents it in this sense, right? So in other words, can we find a matrix A which operates the exact same way, has the exact same properties as the linear transformation L? And so the answer is going to be yes, we can always do that actually. So as long as we're mapping between these vector spaces Rn and Rm. So here's a theorem that we'll state, and then we'll actually prove this theorem, and then from there we'll look at some examples and some consequences of this. So here's the situation. Let's say we have a linear transformation L from Rn to Rm. Remember the notation. L maps Rn to Rm. Let's suppose that this is a linear transformation. Then, in this case, then there exists a matrix, which we'll call A here, sometimes called A sub L, to show that it's representing the matrix here, right? But this, or sorry, that it's representing the linear transformation. This matrix is going to be an m by n matrix, and it obeys the property, so such that L of x, the linear transformation applied to a vector in Rn, is equal to A times x, and this is going to be true for all x in Rn. All right, so we say that this matrix A represents the linear transformation L. So in this case, let's write this down. I'm kind of defining this as we go here, right? But the matrix A is said to represent the linear transformation L. But notice that we can find this matrix for any linear transformation, which means that in some sense a linear transformation is a matrix, right? Is matrix multiplication. Okay, so this is an important theorem. Let's make sure that we can prove this one before we go on and study the consequences of it. But notice that I didn't say anything about a basis up here, right? So we're going to assume that we have the standard bases of Rn and Rm. So let's start our proof right there with the basis. So let's let E1, E2 up to En be the standard basis for Rn. And then we just basically want to apply the linear transformation to these basis vectors. All right, so this is going to be the standard basis of Rn. And then we're going to define a couple of things here. So let's define, these are going to be the columns of the matrix A. They'll end up being the columns of the matrix A, but define Aj to just be L applied to Ej. So we apply L to the basis vectors, and that'll give us n new vectors that live in Rm, right? So these Aj's live in Rm. So this is a vector in Rm. All right, and these are going to be the columns of our matrix. So we define these column vectors, and we put, or define, our matrix A, remember we could call this A sub L, right? To be the matrix whose columns are A sub 1, A sub 2, all the way up through A sub n. And these vectors, so there's n columns, but these vectors live in Rm, right? So each column has m entries. So this is an m by n matrix. It has m rows then. All right? So we've defined the matrix this way. And so this is a constructive proof in that we've just talked about, if this works, right? If we can prove that this indeed behaves the same way as the linear transformation, then we've also learned how to construct a matrix that is guaranteed, right? Because notice the theorem is just existence. It just tells us, okay, there is a matrix. The question of what is the matrix is answered in the proof as long as we can prove that this is the right matrix, right? So let's do that now. So if we have any other vector in Rn, right, a vector x, right, then we can represent it in this basis, right? So this just means that x is equal to x1, e1, its components, right? X2, e2, all the way up through xn, en. So here the x sub 1, x sub 2, etc., those are just the coefficients, right? Those are the entries in the vector, if we wrote it in vector form. And we've written it as a linear combination of the basis vectors, right? And now we can apply our linear transformation to x. So L of x, on one hand, it's going to be L of this expansion, x1, e1 plus x2, e2, all the way up through xn, e sub n. And then we can apply the properties of a linear transformation. We don't know what transformation L is, but we know that it's linear, right? So it has to obey the linearity properties. And the linearity properties say that this L can be distributed in some sense over all the plus signs, right? And then we can factor out all the constant multiples, or the scalar multiples. So this can be written as x1 times L of e1 plus x2 times L of e2 plus all the way up through xnl of e sub n. And this is true by linearity. So this is using the fact that L is a linear transformation, right? So this is by linearity. Now we can sub in, we defined each of these L of e sub I, or e sub j, we called it, right, to actually be the column vectors, right, a sub j. And those are the vectors that ended up in our matrix. So we can make another replacement here. We can write this as x1, a1, plus x2, a2, all the way up through xn, an, all right? And now this can be written, this is now number times vector, right? But this can be written in the following form. If we collect all of the column vectors into a row vector, in other words, we make it a matrix just like this, right? Then we can write this as a1, a2, etc. There's our matrix A, but written as a row vector whose entries are its columns, times the column vector x1, x2 through xn, right? And look at this. This is exactly the matrix A times the vector x in its standard coordinates, right? So this is exactly A times x. And that's what we wanted to prove, right? So we started with L, we applied the definition of the linear transformation. We defined our matrix first, right? We defined the matrix A by defining its columns. And then it turns out that that's exactly the right way to define A, because look at what happened. We got that L of x is equal to A times x for this matrix A. All right, so this is the end of the proof. But we've learned a lot here, right? So let's just recap the most important thing that we learned, which is exactly how to write down a formula for our matrix that represents our linear transformation, all right? So there's the formula, but the most important part of this is this part, right, of how to define the columns of our matrix. So let's recap that. Like I said, let's recap that before we do an example here. But we'll write it this way. So the matrix A that represents L with respect to the standard basis, right? So this is how we've defined the matrix. So we don't have to say too much about this, but it is important though, right? With respect to the standard basis, the basis always matters, right? So this is given by the following formula. So this matrix A is the matrix whose columns are L applied to the basis vectors of the domain space, right, of Rn. So it's L of E1, L of E2, all the way up through L of E sub n. And we just collect those vectors into a matrix. Those become the columns of our matrix A. And that is, by the way, when I say basis, I should, standard basis is always ordered, but it's got to be an ordered basis, right? Because the order, if we change the order of the basis, we're going to change the order of the columns in the matrix A. So the order matters, right? It's an ordered basis. All right, let's try one now. So let's try to actually find the matrix. That's what I mean here when I say try one. So here's an example. Let's suppose that we have a matrix, a linear transformation L that maps from R3 to R2. All right, and it's given by the following formula. L of x, so x comes from R3. That means it has three components, right? I'll write this out a couple different ways. x1, x2, x3. The output of this is just going to be x2 minus x1 in the first component, and x3 minus x2 in the second component. All right, and so I would like to find the matrix representation of this linear transformation. So what do we have to do? We have to apply L to the basis vectors, see what our columns look like, arrange it all into a matrix. So why don't you guys take a moment to work on that, and we'll check back in when you're done. All right, let's see how you did. We kind of gave a hint there as to how to do it before we went to the break there. But we want to apply our matrix L to each of the basis vectors. And so we're going to apply L to 1, 0, 0 first. Just by the formula, x1 is in the first component, right? So this is going to be, we'll just write it out. So it's going to be 0 minus 1, and then 0 minus 0. So the first column of our matrix is going to be negative 1, 0. And then we apply this to each of the other basis vectors, right? So L of E2 is going to be L applied to this one. So this one's going to be 1 minus 0, and then 0 minus 1. So this column will be 1, negative 1. And then we apply L to E3 to get our last column. Right? And so this is going to be 0 minus 0, and then 1 minus 0. So this one's 0, 1. And this tells us then that our matrix A is the matrix for which these are the columns, again, in order, right? In order. So negative 1, 0, 1 minus 1, 0, 1. And so there's the matrix A that represents this linear transformation L. Okay? All right, so there's another there are many important linear transformations, but one of the linear transformations that you guys will see and use frequently in applications are rotation matrices. And so let's work out a formula for the matrix that performs a rotation around the origin. So rotation matrices for this section. So let's start by just kind of setting up the problem here. We want to, again, study rotation about the origin in Rn, but let's do it in R2. So in R2, this is a linear transformation, and we can check that once we have the matrix for sure. But so we want to make, we'll call our linear transformation R sub theta. So the theta matters. The theta is the angle that we're going to rotate. All right, and this is going to map from R2 to R2. So it's a linear operator. Remember, we call it an operator when it acts on a space. If the domain and the codomain are the same space, right? And so here is our R2 coordinate axis. What we need to do is know exactly what happens to the basis vectors, right? So let's think about the two basis vectors, E1 and E2. These are the standard basis vectors, and we want to rotate each of these by an angle theta. And this is going to work exactly as it works in trigonometry, right? The angles are going to start in the positive x-axis direction, so x1 direction, and it's going to open in the positive math direction, which is counterclockwise, right? So we're going to apply our rotation of theta, and we want to see what the result is, okay? And then find the components of these things. So here's our copy of the domain space of R2, and the codomain I'm thinking of as a different space, right? A different copy of the same space. So after we've done this, we've rotated, say, an angle of about this much. So the idea here is that this is the angle theta that we've rotated, and this red vector is now R sub theta of E1. So that's the output, right? The blue vector, E2, is going to rotate the same amount. So it's going to be, and it's these are both supposed to be unit vectors. So, you know, we always have to take my drawing with a little bit of a grain of salt. But so this is R of theta of E2. And so we want to figure out exactly what are the components of these new vectors, right? So to make our matrix, we have to apply the rotation transformation to the basis vectors. And so whatever the coordinates of this red vector are, that'll be our first column. And the coordinates of the blue vector will be our second column, right? So here's how we do it. Notice that, of course, these vectors are unit vectors, and we've just rotated around the origin, right? So if I had drawn them correctly, then they should lie, their endpoints, right? Their terminal points should lie on the unit circle. And so really all we need to do here is we need to identify what are the coordinates of the terminal points, because these are in standard position, obviously, right? These vectors are in standard position. So we need to identify these coordinates of the terminal points. So this one's in quadrant 1, the way I've drawn it. So I'm doing a small rotation just to get an idea of how this works, and then it turns out that it works for any angle theta. But as far as we're concerned right now, let's just start with this small rotation. All right? And because this is still in the first quadrant, we know exactly what the coordinates of this are, right? The coordinates of this are cosine of theta and sine of theta. All right, cosine of theta and sine of theta. All right, what about this one over here? So this one has been rotated into the second quadrant, all right? And the reference angle, if we remember our trigonometry, the reference angle is actually this one, right? So this is the reference angle. And the reference angle here is actually pi over 2 minus theta, because it's the complementary angle to the angle theta. So the reference angle is this one. We also know that the x value is negative over here, right? And the y value is still positive in quadrant 2. And so I'm going to write this down here just so I have more room. But for this blue vector, r theta of E2, which is in now quadrant 2, this one's going to be, remember how this works with the reference angle, it's going to be cosine and sine of the reference angle, but then the sine, S-I-G-N-E, S-I-G-N sign, that one depends on the quadrant, right? So in quadrant 2, we've already said this, the x value is negative and the y value is positive, right? So this is going to be negative cosine of pi over 2 minus theta, all right? And this one up here is going to be positive sine of pi over 2 minus theta. All right, but these are now our cofunction identities. These are going to be cofunction identities here. So these are exactly correct based on the reference angle, but we don't want this angle pi over 2 minus theta in here. That's not the same angle, right? That's not the same angle as the one that we're looking at. So I hope we remember our cofunction identities, which say that the cosine of pi over 2 minus theta is just the same as sine of theta, right? And same thing with sine. The sine of pi over 2 minus theta is the cosine of theta. All right, those are the cofunction identities from trigonometry. So this one ends up being just minus sine of theta, and this one's positive cosine of theta. And those are the coordinates of E2. And so now we've got our coordinate vectors. They're all in terms of theta, right? We've applied it to our basis vectors. And so we put these together now to make our matrix. So I'm going to call the matrix r theta as well as the transformation. So just for the, it's a little confusing, but just for the sake of making sure that this looks like rotation by theta, I'm going to call it the same thing, right? So the matrix is going to be the first column, cosine theta, sine theta, the second column, minus sine of theta, cosine theta. And so this is the matrix which, when applied to any vector in R2 will rotate that vector around the origin by an angle of theta. So this is the matrix representation, right, of that rotation matrix. So let's put a box around this. This is an important one. We can just remember this. You don't have to derive it every time. That's kind of the nice thing about deriving it once and having a general formula for a general angle theta. You don't have to do it again, right? You just do it once. All right? Before we move on to, other stuff, let's think about the following. So a linear transformation that rotates by an angle theta, this is going to be non-singular, right? Because we can undo that rotation. What would be the inverse transformation of a rotation by an angle theta? So if we want to undo a rotation, what do we do? Well, we just rotate again, right, by the angle minus theta. Okay, so the inverse transformation the inverse transformation, just geometrically thinking, right? If we just think about it geometrically, if you rotate something by an angle of theta, you want to undo it, you just rotate the other direction, right? So that's going to be an angle of minus theta. But the inverse transformation of r theta should be, right, r sub minus theta, which I'll put in parentheses like this. Let's make sure. So let's just, because if the transformation is the inverse, then the matrix should be the inverse matrix as well, right? So r minus theta, the question now that we want to verify, right, is r of minus theta. Does this equal r theta inverse? Question mark. Okay, so that's the question. So let's work it out. So r sub minus theta, this is going to be the matrix, right? Just given by, if we just compare with the formula, the general formula for a rotation matrix, it's going to be the matrix where the theta is replaced by a minus theta. So this will be cosine of minus theta, sine of minus theta in the first column, minus sine of minus theta, and cosine of minus theta in the second column. All right, and then we remember that our cosine function is an even function, right? So that even functions eat their minus signs. So this is just cosine of theta. And then sine is an odd function, right? So the minus sign comes out. So this one's going to be minus sine theta down here and minus minus. So positive sine theta up here. And so this is the rotation matrix for rotating by an angle minus theta. Now we want to make sure that that's really the inverse. So what do we have to do? Well, we have to multiply them together, right? So now we multiply r theta times r sub minus theta, and we just see what happens. So this one's cosine theta, sine theta. Again, I'm doing r theta first on the left. Minus sine theta, cosine theta. I guess that's backwards from the way I described it, right? So in this one, we're rotating by minus theta first and then by theta, but it's the same idea. We just replace minus theta with theta. And then this one's going to be sine theta, cosine theta here. All right, and as we multiply this out, look what we get. We get in the first component cosine squared theta plus sine squared theta minus minus. The second, the 1, 2 component down here, 2, 1 it is actually, right, is sine theta cosine theta minus cosine theta sine theta, so that's 0. And then same thing up here. So this one is going to be cosine theta sine theta minus sine theta cosine theta, so that's 0. And then down here, this one's going to be sine squared theta plus cosine squared theta. And of course, by Pythagorean identity, this matrix is these are 1, right? Cosine squared plus sine squared is always 1. All right, so that is the identity. So the inverse transformation of r theta is r sub minus theta. And so there's a geometric way to derive the inverse of this transformation, the inverse matrix as well, right? Okay, so now let's move on to general vector spaces. Okay, so let's suppose that we want to define a matrix. We want to find a matrix that represents a linear transformation between general vector spaces. So let's write it this way. Let's let L be a linear transformation between vector spaces V and W. So this is a linear transformation of what we'll call abstract vector spaces. But these are going to be finite dimensional. So let's suppose that the dimension of V is equal to n, and the dimension of W is equal to m. All right, so that we're working kind of in the same realm here, that we have an n-dimensional vector space being mapped to an m-dimensional vector space. And let's further suppose that we have ordered bases of these two vector spaces. So further, let's call it E be a basis V1 to Vn, ordered basis, and we'll call this one F. This one's going to be W1 up through Wm. Let these be ordered bases of V and W respectively. Then we want to do the same thing, right? We want to find a matrix that represents this linear transformation from V to W with respect to these ordered bases. All right, so this is kind of like an extension of the last theorem, but I won't write it as a theorem, but there exists, here's the key, okay? There exists a matrix A, and it's again going to be an m by n matrix, okay? And it obeys the following property. So we would like it to be that L of V, or L of X in some sense, is equal to A times X, right? But we have to make sure that these are abstract vector spaces. So we have to make sure that this is done in coordinates, okay? In coordinates. So here's what we have. We want L of X, but this is going to be written in W coordinates. So that was our basis F, right? So L of X in our F basis coordinates is going to be equal to the matrix times X in its V coordinates, or its E basis coordinates. And this is going to be true for all X in our vector space V. Okay, so the point here is that we can do exactly what we did up here with the previous theorem. We could write all of this out in exactly the same way, and it's going to be defined exactly the same way. I'll write it out in a moment, but we're going to define the matrix the exact same way. We just have to first define our coordinates, right? Define our basis, and then write everything in coordinates. And the nice thing about coordinates, which we talked about in a previous lecture, is that we can turn any finite dimensional vector space, essentially, into a copy of Rn or Rm or whatever, just by writing it in coordinates. And then you just have to keep track of your basis off to the side so that you can go back to that basis when necessary, right? When you can go back to the abstract vectors when it's necessary. So the matrix is going to be obtained in the same exact way here. So the matrix A is defined as follows. Again, we need to define its columns, right? So what are we going to do? We're going to apply L to each of the basis vectors of V. So the basis vectors in this set E. We're going to apply L to each one of those basis vectors. Write the output in F coordinates, the way I've written it here, right? So in W's coordinates, but in F coordinates, and then just arrange those into a matrix. So this matrix A is defined to be, the first column is L of V1, again in F coordinates. The second one is L of V2 in F coordinates, and this continues on until we get to our last one, L of Vn in F coordinates. Okay, and so that's how we build our matrix A, which is going to be a representation of our linear transformation from V to W. So let's see exactly how this works in a diagram form. On one hand, up here, I'm going to draw a couple different representations here. So we have our matrix L, we have our linear transformation L that maps from V to W, right? So it takes this vector V, and L maps this way, and it outputs, right? It returns L of V, which is equal to, we'll say, W in the vector space W. All right, well, what does the matrix do? Well, the first thing that it does is we want to first change our coordinates, right? So we first, I won't name this, but we change our coordinates down here. We write, in other words, not change, but we write our matrix, our vector V in coordinates. So this is now living in Rn, right? The coordinate vector lives in Rn. The dimension of V is n. Then we apply our matrix A by multiplication, and A times V, this is going to be equal to the coordinate, the F coordinate vector for the same vector W here. So this is in Rm. And on the two outsides, those can be just interchanged, right? So just by writing in coordinates. And so the matrix A and the linear transformation L are the same mapping. One of them is from V to W, the other one's from Rn to Rm, right? But if we match up the coordinates, then this is exactly the diagram that we're looking at, okay? So they do the exact same thing in this sense. All right, so let's look at an example now with abstract vector spaces. So this will be item 6 of the lecture. Let's consider this following space here. So this is going to be a subspace of continuous functions, but I'm going to define the basis. So this is going to be the span of sine theta and cosine theta. And let's consider this to be an ordered basis. So sine first, then cosine. And this is, of course, a subspace of continuous functions. All right, but they're also continuously differentiable functions, so they're actually in C infinity if we want, right? C infinity on any interval from A to B. And let's remember that the derivative operator is linear, right? So let's define, or just remember here, but define an operator D, which maps from this subspace back to itself by the following. So it takes a function f that's in this space and maps it to f prime. Just takes the derivative, right? Then we want to find the matrix that represents this transformation. So we can find a matrix here. So that's our goal here, right? So find the matrix that represents D on this space, the subspace S. All right, so the first thing you want to do is define your coordinates, then apply the derivative to each basis vector, and then write the answer in coordinates as well, and then build your matrix. So I'm going to give you guys a moment to try that one on your own, and then we'll check back together. All right, let's see how you did. So let's first start by taking the derivative of our basis vectors. So we'll take D and apply it to sine of theta. That's our first basis vector. Of course, the derivative of sine is cosine of theta, right? And then we'll apply down here the derivative to cosine of theta, the second basis vector. And that's, of course, minus sine of theta. Now, we want to write these in coordinates, right? And the coordinates come from this ordered basis here. So this is going to be 0 sine theta plus 1 cosine theta. And so in coordinates, this is the vector 0, 1, right? 0, 1. The second one, this is going to be negative 1 times sine theta plus 0 times cosine of theta. So in coordinates, that's the vector negative 1, 0. All right, and these are just the columns of our matrix. So our matrix A that represents this derivative operation, this is going to be the matrix 0, 1, negative 1, 0. This is with respect to the ordered basis, sine theta, cosine theta. If you switch the order of these and put cosine first and then sine, then actually it changes two things, right? It switches the columns, but it also switches the rows. Okay, so it's kind of like a transpose, actually, for this one. All right, let's notice something else here. So let's notice that if we multiply AD times itself, so that's equivalent to taking two derivatives, right? So AD squared equals AD squared, that's correct. But AD squared, which is AD times itself, right? This is the matrix then, 0, 1, negative 1, 0, times itself, 0, 1, negative 1, 0. And look what we get. We get a matrix back that's negative 1, 0 in the first row, and then the second row is going to be 0, negative 1. Or it's equal to minus the identity matrix, right? So this says then that taking two derivatives on this space is the same as applying a minus identity operation on here, right? Just changing the sign to a minus sign. And so what this means then, this is a consequence, right? But then all functions in this space, all the functions in S are solutions then. So these are all solutions of the differential equation that basically obeys the same property as the matrices, right? So that obeys the following. So I'm going to write it in I'm going to write it in matrix form first, but AD squared plus I times F. Now let's put it in coordinates. So times this coordinate vector is equal to the 0 vector, right? So there's the matrix representation of it. But in function notation, this is just going to say two derivatives plus the function itself, right? So, or this differential equation, y double prime plus y is equal to the 0 function. Okay, so actually, if you guys haven't taken a differential equations course yet, you're going to actually use a lot of linear algebra, maybe without even knowing it, right? Because this is called then the fundamental solution set for this differential equation. Basically, it's linear combinations of these basis vectors, which we know that that's what they are, right? Basis vectors of this vector space. There's a vector space of solutions of this differential equation. All right, so let's talk about now that we've talked about how to represent different linear transformations on abstract vector spaces by matrices by choosing ordered bases, right? Then let's talk about what's the consequence of changing the basis, or what happens to the matrix if we have two people go into different rooms and choose different bases for their vector spaces. Well, you would imagine, we've already talked about it a little bit, right, that you're going to get different matrices back. Okay, so let's suppose the following, let's consider the following situation, but first let's say this. So first of all, let's write it down. Matrix representations are dependent on a choice of ordered basis, right? So they depend heavily on a choice of ordered bases. Bases, really, one for each space, right? All right, so let's suppose that we have a linear transformation from one space to itself, so a linear operator here. So let's let L be a linear transformation from Rn to Rn, and let's suppose that we have two different bases for Rn as well, ordered bases. All right, so we'll name these U and V. So let's say U is a basis U1 to Un, and V be this ordered basis set V1 to Vn. Let these be ordered bases. And similarly, let's let S be the change of coordinates matrix from U to V. So this be the change of coordinates. All right, so change of coordinates is itself a transformation, a linear transformation, which if you think about, that makes perfect sense, right? But it's linear transformation, and it's a non-singular matrix, right? So this matrix S is going to be non-singular. So let's let A be the matrix that represents L with respect to the basis U. So with respect to the basis U, and then let's let B be the matrix with respect to the basis V. So the matrix B is going to be the matrix representing L with respect to the basis V. So we have two things going on here, right? So on one hand we have, let's say L, I'll write it this way. L is going to map a vector X to L of X, right? That's just how L behaves. That's the linear transformation itself. In matrix form, though, we're going to have two different situations. So we're going to have our matrix, our X coordinate, so our U coordinates here of X, that's going to get mapped to the U coordinates of A times X, right? Let's call it Y. Let's write that up here. So let's say that L maps X to Y. And then down here we can just write this as Y. And this Y is also going to be in U coordinates, and A does that mapping. But at the same time, if X is given in V coordinates, then B, right, is going to map to it's going to map the V coordinates of X to the V coordinates of Y. All right, and so we've got these two situations happening simultaneously, but notice that on the left and the right-hand side, the vertical sides here, these are just going to be the change of coordinates matrices. So remember, our matrix S is going to change from U to V. So we could say that one goes this way, right? And on the other hand, over here we have, like, maybe if we want to go from V back to U, then this would be S inverse, right? And so we could say then that multiplying A times X is the same as multiplying by first S, then B, then S inverse. So as matrices in this situation, then A is going to be equal to, first multiplying by S, remember we go from right to left when we write these down. So first changing to V coordinates, then applying transformation B, and then changing back to your U coordinates, right? So this property right here, these two matrices represent the same linear transformation. S is the change of coordinates, right? And then these two matrices, A and B, are related by this equation, right? So this equation relates the two different matrix representations of L. All right, so we give this whole situation a name. So we say that two matrices that are square, these are both square matrices, right? They're mapping Rn to Rn. So two matrices, A and B, in Rn by n, these are said to be similar. They are similar if and only if there exists a non-singular matrix S. Notice that A or B individually could be singular in this case, right? But S has to be non-singular. It's also got to be an n by n matrix such that the following is true. So such that either A is equal to S inverse BS, or you could switch the roles, right? We could have rearranged everything here, but this is the way we've got it here. Notice though that there is definitely another way we could write this. If this S is non-singular, so if we multiply S on the left, sometimes you'll see similarity defined by the following equation, that S times A is equal to B times S. So left multiplication by one matrix is equal to right multiplication by the other. So either one of these can be used, but this first one is our definition though. S inverse BS, that's the definition of similar matrices. So these two matrices represent the same transformation with respect to different bases. That's the idea here. So in the S matrix is thought of as the change of coordinate matrix for this transformation, or for this space. Okay, so let's do some more examples now, and just a couple more examples, and then we'll call this lecture. But this first one I would like to do the following. So find the matrices that represent the derivative operator. So we've already talked about the derivative operator, right? So the derivative operator is D. This is going to map, let's say, from P3 to P3 for the sake of this, because I want this to be square. As we know, the derivative operator is going to take polynomials in P3 and map them down to P2, but that's okay. We'll map them to P3 with respect to two different bases. So with respect to the bases, the following bases. The first one, they're ordered bases, right? So I'll write them 1x squared. That's the standard basis of P3. I'm ordering it this way. So one, counting up in the degree of the polynomials. And then the other one, so we'll call this one E. And then we'll call this other one F. This one, I'm going to just tell you, is a basis. You would obviously want to check this in general, but 1, 2x, and then 4x squared minus 2. All right, but let's find the derivative, the matrices for the derivative operator for each of these two bases. And so for this one, you can just compute them directly, but then you'll see that they're going to be different. So work that out, and I'll be back in just a moment. All right, let's see how you did. Let's take first with E, all right, so with this E basis, this one's going to be very straightforward. We'll just take the derivative of each basis vector. Derivative of 1 is 0, and so in coordinates, that's the 0 vector. That's pretty straightforward. The derivative of x is 1, and so again, this is 1 times 1 plus 0 times x plus 0 times x squared in this order. So this is the vector 1, 0, 0. And then finally, the derivative of x squared is 2x, right? And so this is going to be 0 times 1 plus 2 times x plus 0 times x squared. And so in coordinates, this one's going to be 0, 2, 0. And so the matrix that represents our derivative, let's just write this matrix as D as well. But we'll do it as D sub E so that we know that there's a basis here. This matrix is going to be 0, 0, 0 in the first column, 1, 0, 0 in the second column, and 0, 2, 0 in the third column. All right. And let's now take the same approach for the second basis, right? So we already know what happens to 1. The derivative of that is 0. The 0 vector is the 0 vector in every basis, right? So that's just 0. We now need to take the derivative of 2x, which is of course 2. And so that's going to be 2 times 1 plus 0 times 2x. Notice we have to use this basis now. Plus 0 times 4x squared minus 2. And so that's the vector 2, 0, 0. Right? And then finally we take the derivative of, when you take the derivative it's all the same, right? It's just basic calculus. But when you take this derivative, this is now 8x. All right, so this one's going to be 0 times 1. It's then going to be 4 times 2x, right? 4 times 2x. We have to get it in the same basis. This is 8x, right? So 4 times 2x plus 0 times 4x squared minus 2. And so this one in coordinates, I should have written this with the coordinate brackets. This one in coordinates is going to be 0, 4, 0. All right, so this tells us then that the matrix representing the derivative operator with respect to this second basis, this other basis, is going to be 0, 0, 0, 2, 0, 0, 0, 4, 0. So these are obviously not that far off from each other, but they're different. The point is that they're definitely different, right? They're absolutely different. Okay, so let's do one more example, and then we'll leave this lecture as it is. So let's consider the following situation. This is item number 9 here. Let's let L map, in this case, R3 to R3. So this is a linear operator on R3. Let's define this by the following. So L of x is going to be defined by a matrix transformation, or matrix multiplication, where we'll give you the matrix here. So the matrix A is going to be the matrix 2, 1, 1, 2, 1, 1. So it does the same thing to the first two basis vectors, and then 0, 2, 2. All right. So this is the matrix representing A with respect to the standard basis, you could say. And so I want to know, can we find the matrix? So find the matrix that represents the same transformation with respect to the following basis. So this basis is going to be, we'll call it y, y1, y2, y3. And so these basis vectors, y1 is going to be the vector 1, negative 1, 0. y2 is going to be the vector negative 2, 1, 1. And y3 is going to be the vector 1, 1, 1. All right, so we'd like to find the matrix representation of the same transformation L here with respect to this new basis, this basis y. So why don't you take a moment to think about that, and then when you come back, we will finish this one off together. All right, so for this one, we could use the properties of similarity, so the definition of similarity if we want, right? We can always do this. So one way is we can just define our new matrix. We can call it, say, B, our new matrix B, to be exactly this y inverse. So remember, the change of coordinates matrix for given this basis, right, between the basis y and the standard basis is just the matrix that you get by kind of removing the decorations from here, right? So this is going to be then y inverse a y, where y is the matrix that comes from this new basis, right? So it's a change of coordinate matrix for this new basis. So that's one way, but that requires us to actually find the inverse matrix of y and then do some matrix multiplication. There's nothing wrong with that at all, okay? But another way is to just apply A to the basis vectors and see if we can solve the system of equations simply, right, to get them in the new coordinates. So let's apply L to y1, And so L times y1 is going to be A times y1, and that'll put it in standard coordinates, right? So let's see what it does. So A times y1 is 2, 1, 1, 2, 1, 1, 0, 2, 2, times y1, which is 1 minus 1, 0. All right, and so this one's going to be 2 minus 2 plus 0, so that's 0. This one's going to be 1 minus 1 plus 0, that's 0. 1 minus 1, 0. Okay, that's easy, right? So the 0 vector, as we said, is the same in all coordinate systems. So L of y1, the first column of our matrix, is just going to be the 0 vector. So that's good. Now we apply the same reasoning to each of the other vectors. So A times y2, 2, 1, 1, 2, 1, 1, 0, 2, 2. This one's applied to negative 2, 1, 1. Right? And we just multiply. So this is going to be negative 4 plus 2. So that's negative 2. This one's going to be negative 2 plus 1 plus 2. So negative 2 plus 1 plus 2, that's 1. Same thing here, right? It's the same row, so that's also a 1. And so that's itself, right? So in coordinates, what's that? Well, it's 0 times, I'll just write these in these terms, 0 times y1 plus 1 times y2, it gave back itself, right? Plus 0 times y3. So in y coordinates, this is going to be the vector 0, 1, 0. Right? You make sure you get it in y coordinates to make the matrix. And then we just finish this by doing the same thing with y3. Since the first two were so simple, even if this one's a little more complicated, we just, it's going to be worth the effort, and it's going to be, we've already come this far, right? But it's going to be less work than trying to compute the inverse matrix at this point. Again, there's nothing wrong with that if that's the way you did it. But this one's going to be 4. This one is going to also be 4 and then 4, right? So actually this is not that hard because this is 4 times the vector 1, 1, 1. So this is 0 times y1 plus 0 times y2 plus, in this case, 4 times y3. And so in coordinates, this one is 0, 0, 4, right? And so this means that our matrix B is equal to 0, 0, 0, 0, 1, 0, 0, 0, 4. Okay, so that's how this works. So these, by the way, that means that A and B are similar. I think I forgot to write this down, but the symbol for similarity is just a squiggle. A is similar to B. So how do we know that? Because we got them, right, by applying the same transformation to two different bases. So they have to be similar. But you could also have worked out the change of coordinates map or matrix and multiplied it all out and found y explicitly that way if you wanted, right? But I'm going to leave this one here, and I'll see you guys in the next lecture.